Oops. Part of today to talk about the TBL. So you give the so we put up a couple of new questions on this year's TBL, and the reason we did that was well, actually for a number of reasons. So remember when you went out to down to the beach and you did a magnetometer profiling over a body, and then you actually buried a sphere or buried a rod that was down like this. You didn't acquire the data, but we showed you what the data were for that, and they were just like, if you look in plan view over the map, they just kind of look like a big bullseye. So that was a data map that you get from something out in the field. When you did the case history, there's this region where they had a whole bunch of these old wells, and they were actually causing problems, and a couple of people died. And so they needed to find these guys, and they are just like this. They've got some kind of a well target like that. So what we wanted to do was to kind of combine those along with the GPG and the apps, and just kind of put it all together. So like you have a way of investigating the same problem by kind of thinking what happened in the field, by reading the case history, by looking at the GPG, and by using an app. So this seems like the ideal way to do that. In the end, we neglected to, well, it was simple, but it was a bit fiddly, and that caused some people problems. There were a couple of groups that actually completed this, and for anybody who did, you get that awesome mark. For anybody who didn't, what we're going to do is just kind of forget about the two questions that have to do with the details. They're questions 9 and 10. So we're not going to mark those for you. If you did them, you get bonus marks, but if you didn't, we're not going to mark them. But what I did want to do here was to kind of take you through what is happening, because I think what this will do in 15 minutes, we can kind of consolidate everything and you'll understand, and we will be good to go. So let's look first of all at this this first point up here. So we've got a magnetic field that's coming in, right? And we've got a body that's sitting here that looks like this. One of the first things I asked you to do was to sketch the charge that would be observed on that. So first of all, let's just talk a little bit about that. If I've got some kind of a body here, looks like this, and if I put a magnetic field on it like this, then what do I get for a magnetization? And how do I describe it? So first of all, which direction does this get magnetized in, Hannah? They get magnetized down, right? So there's a magnetization that's in the same direction as H naught and depends upon H naught. And then what is the other thing that gives rise to the strength of the magnetization? Kelsey? No, let's just assume it's all down like this. What's that relationship between the magnetization and the magnetic field? Yeah, so it's the magnetic susceptibility. So that tells us the magnetization. And that is independent of any direction that this object is in. If the object was like this, then it's going to get magnetized like this. So here's the magnetic field. So the magnetization is always in that direction of your field. Okay? That's point number one, and this is the relationship. Point number two was that we talked about magnetic charges that were built up, and the way I introduced that was that, I mean, you can think about, you know, any earth material divided up into a whole bunch of little elements here, and each of these guys being a little magnet. So I put a big magnetic field on here. Each of these guys kind of gets magnetized, so I think you can see that. And then you can think about, well, at each of these boundaries here, so this is a positive and a negative charge that are used in here. So I've got a negative charge here, positive, negative, positive. So these guys kind of cancel. At the end of the day, the only thing I'm left with are negative charges on the top and positive charges on the bottom. Okay? Now, there's a way of evaluating that, and it gives us this thing called the charge density was equal to the magnetization dotted into the unit normal. So this is the other important piece of information that we have, and it says here that, well, the normal is the outward directing vector, so that on here, on this guy here, the outward normal is like this, and it's like this, that, and it's like that. So if we were to look at what is happening at the top here, so what sign of charge would we have if it's sitting up on here?
Have the negative charges up top?
Yeah, we're just going to have negative charges on here because M is in this direction, M is in that direction, so they're opposite. So it's going to be negative. So I get a negative charge up here, and conversely, then, Liam, what do we get down here? I'm going to get a positive charge. And what do I get on the outside here, Lucas? I get 0. So the only charge I get is wherever this magnetization crosses the boundary. So now you can figure out on here, so here's the pipe here, and then what am I going to get? I'm going to get, Kelsey, yeah? I'm going to get negative on here and positive on here. If I change the orientation and I make it like this, then what do I get on top here, Al?
Sort of negative on the top.
Negative on the top, and on the side?
It's kind of negative on the top side.
Kind of negative, right? And here?
Positive at the bottom, it's sort of on the bottom.
Yeah. So now what I'm doing, because the magnetization is still this direction, I'm just kind of redistributing the charge. Now the really interesting thing, and this is what kind of ties all this stuff together, if I put this to be like this, okay, now I've got a cylinder that looks like a pipe, things really simplify, right? Because what do I have on the top side here? Anna? I'm just going to have negatives here, nothing here, and then I've just got positives on the bottom. So now we have like basically a pole here and a pole here, and then that is going to make my my final distribution. And if I make this guy long enough, okay, then the only thing that I actually see is this guy here, and that then becomes a monopole. Okay, so that's how all of that fits in. So you're to sketch the charges. So people do that. And then if you've got a charge, maybe the other thing, so we've got a charge here plus Q, okay? So which way do the field lines go from that? John?
Out.
Well, you don't really look like John, but you know.
It's not today.
It's John's name. That's good. Fair enough. So they're going to go. Positive charge is just going to go up. So now it's interesting. Let's just kind of sketch out what you'd obtain if you did a total field anomaly over this. So now remember, with a total field anomaly, you're just going to measure the component that's in the direction of the Earth's field. So let's suppose that the Earth's field is still like this, not this way, but we end up, somehow I have a positive charge here. Then what are we actually going to measure? If we're sitting here, for instance, are we going to get Rachel? Is it Rachel? Or Raquel? Greg by Hannah.
Yeah.
Rachel or Raquel? In negative, right? And then as we come out here, we're going to get smaller and smaller values. So it's just going to go like that. So our anomaly is going to be looking like that. And then if we looked at the map, in fact, we can do that. So on this, there's a monopole option. So we have dipoles, we have a monopole, and if we have a positive value,
can you refresh that? It seems like it.
seems like it's kind of a,
Oh, so just restrict that. I think it's gone. No, go back to GPG and rerun.
yeah.
Yeah, GPG.
Okay, so let's try this again. So now we're going to put in a positive charge. Thank you. So we put in a positive charge, and we're measuring the total field anomaly, and you notice that it is negative here, right? So that's all in accordance with it. Now, if I put in a negative charge, then which way do the lines go? Raphael? Pardon me? Negative charge, which way do the lines of field go? In towards it, right. So the field lines now look like this. Okay? So now if I'm sitting up here, what my total field anomaly is going to be what? It's going to be positive, and then it's going to go off like this, right? So now if I do that here, if I make it negative, you see that we've got some positive charge there. Okay, so all of this is now kind of starting to fit together. And then what I asked you to do on here was to compute. So now we kind of got everything set up here. We just need to kind of compute the charge. So we have a charge density, which is like the charge per unit area. So the charge, the name for the charge is a Weber. So that's a Weber per meter squared. And that's the charge density. So in order to find the total charge, then what do we need to do? Is it intisar? Okay, so we've got the charge density and we got this pipe. Remember the pipe is like this. Right, so it had an inner and an outer radius. This was 10 centimeters, and the inner radius was 9 centimeters. So, how do we get the total charge? Perfect. So that's the area. Okay. So what's the formula for the area of the circle? So pi r squared is the area of the circle. So if we want to get this area in here, then that area is going to be this one minus that one. So it's pi, 10 squared, the other one, minus pi 9 squared, which gives us 81 pi. And that is centimeters squared, right? When you're working, you're going to have to kind of work in constant units. So this is, if we're going to convert this to meters squared, how do we convert centimeters to meters? So 81 pi, pardon me? Oh, yeah, thank you. So, and if we were to convert this to meters squared,
Just divide it by 100 squared.
so that's right, so 1 centimeter is equal to 10 to the minus 2 meters. So that means that we've got like 10 to the minus 4. So that's the area. Okay? So now we kind of have virtually all of the things that we need to do. So we've got the area, we multiply. Oh, we haven't kind of figured out m yet. There's one thing that we need to do. This is why in a revised version of this question, I'm going to give you a little bit more feedback. So first of all, how do we have m, and we have the kappa was equal to 150. That's fine. We know h naught. You're given E naught, and here's something that's worthwhile mentioning. So mu naught. So here's the relationship between H naught and B naught. We sometimes, as I said right at the beginning, kind of talk about both of these things kind of being magnetic field, and we'll kind of loosely use that jargon. But when we're actually trying to figure out magnetization, then it's this guy here that we need. And if we're given this quantity, B naught, okay, then to find H naught, we need to convert. So H naught is equal to B naught over mu naught, and B naught, what was it, 55,000 nanoteslas, okay, it's 10 minus 9. And mu naught is just this constant 4 pi times 10 to the minus 7. So that's a nanotesla. If we're, what's the relationship between a nanotesla and a Tesla? 10 to the minus 9, right? So if we're going to convert this to Teslas, then we'd have this as 10 to the minus 9 Teslas. That's 4 pi, 10 to the minus 7 here. So this is equal to 55,000. These things go with a 10 to the minus 2 and a 4 pi. So this 10 to the minus 2 gets kind of rid of that. And 4 pi, I think that's going to give us about 44 amps per meter. Okay, so now we've got H naught. That gives us the magnetization. when we know that this guy here is 150 degrees. So those are a lot of kind of small relationships, but they're actually all important. The important ones being, if you're given B, but you need H, then you've got to have this quantity here divided by mu naught. And H naught is related to the magnetization through the susceptibility, and tau is related to the magnetization with the moment. So you kind of put all of those things together, and they ended up with a Q. So Q, your total charge, was equal, so it's tau times this area, which we have back there, and we put it all together, that's minus 39 vectors. So that is as the charge. Now, if you look in the GPG, is and we look under principles, and we look under magnetic charges. So working with charges, so all of that's here. So here's your tau, and then here's your charge, which is magnetization times the area. And then you're given also that the magnetic field that comes from a particular charge is given by this formula here. So there was a couple of people that got a little confused about that. But actually, let me just write this down. All right. So here was the total magnetic field. So that point charge here, right, and fields are going out or in, positive, negative, then the magnetic field drops off as 1 over r squared. So let's put all of this stuff together, and we've got a Q of this. So if we take B, T, and if we just do all of things, the only thing that tripped people up was the Z and the R squared. I'm not sure that that was explained 100% in the GPG, but you're sitting here, and the whole idea is that things are falling off as 1 upon r squared. So r is the distance that you are out, so r is any distance. If you're sitting up here, r goes out in that direction, and the quantity, well, this is z, and this is x, and this is r. So if you're sitting right above here, z is equal to r. So z is equal to r. You had everything at 1 meter. So effectively, all of this stuff goes, and then you put this material, or calculate this formula, and you ended up that this was equal to 3,900 nanotests. So that's what you should get. So it's a number of steps, but in kind of going through these steps, each one of you kind of thinking like a physical principle, which is kind of good. And we now have a number. If I took this pipe, it had a magnetic susceptibility of 150, had the Earth's field coming down on it, it would get a charge. I'd be able to compute that, and I'd be able to compute the magnetic field from 1 meter above. Okay? How cool is that? We've actually done it. Now what we'd like to do is check. So we can now go back to the app, and we're going to just see. So in the app, you have to put in a moment. Now for a monopole, the moment is just equal to the charge. and we've already evaluated that charge at 39. So if I take the app and I run a monopole with a negative charge, and I have to now bury it, so I want to be 1 meter below. Danielle, did you have a question? No. So I want to be 1 meter below I want to be 1 meter away from the top, which means actually that this pipe has to be buried right at the surface because I'm acquiring data 1 meter above it. Okay, so that means that in the app, I need to set the depth where equal to 0. Okay, so that puts it right at the surface, but I'm like 1 meter away.
Yeah, it seems like it's gone, so probably can start.
Do I have to do the whole thing again?
Yeah. It's annoying.
So back to GPG?
Yeah, back to GPG.
It's annoying. Okay, well, you'll see how these work. So we press the dipole applet, we launch the binder, and we wait. It spins around. Okay, and we're going to run everything. And we get this. Okay, so now we go back, we do the monopole, and negative charge, and we're going to do the depth at 0. I get this. So what's happened here? Let's see. Rita, Soggy kept asking you. What have we got in this guy here? What's unsatisfactory about that? That's a good point. Let's change that to 39. That's not what I was thinking, but that does it. What? The data spacing, yes, 2 meters. Remember, it's buried right at the surface, right? So I've got something here. I'm just measuring right over here. So if I'm if the first measurement is over here, I'm like a long way away. So data spacing should be decreased. What's a good value? Right at the surface. Oh, remember, here's the way to think about it. So remember the depth of burial, okay, was, so if we had the half width, so if we look at this, that for a monopole, it's half of this guy, right? So if we took W half, then the depth of burial is equal to W half over 2. So this is sitting, we're 1 meter below. So that means this is probably going to be 2 meters wide, which means we want to have, I guess, 1 point per 2 meters is enough, or should we have more? Or, yeah, okay, anyway, so, yeah, I mean, if you're going to try to sample that, you want like 3 or 4 points. So let's make that, well, we can even make it 10 centimeters. That's really small. Okay, and now we get this. What's wrong with this? So you are? Pardon me?
Tyler.
Tyler, okay. You guys need your signs. Okay, Tyler.
Let's change now.
So what's wrong with that plot? What's wrong with? What do we need? We're using the app. We want to get some information out of it. What's not quite right? Yes.
You need like zoom in.
Right. And how do we zoom in with the app?
Great question.
Quentin.
Yes.
How do we zoom in with the app?
Make sure you just increase the distance.
Now, if the data spacing is just how often I take the, yeah, so I've just decreased it to 10 centimeters. So I've got good resolution, no question. I've got 10 points over there. Yeah.
So we increase the length.
That's right. So my survey is way too big, right? This is 72 meters. So it's 72 meters from here to here. Right? This guy's sitting there. I mean, I've got the wrong scale. I should be, more like 5 meters or something. So let's just change the scale down to more like. So there's 9 meters. I can make it 6. Okay, so now we're cooking. Okay, so that's now what things are looking like. And notice also the half width. The half width is 1.6 meters. 1.6 meters. And we said, oh, half of that. So it's about a meter below, which is cool, right? That's right on. Now let's just look at the amplitude. So when I did the amplitude calculation, it said 3,900 nanoteslas. And what's this? 3,870. Wow. Well, you got to thank Stoggy because he built the app, right? Okay, but I mean, do you realize kind of like how cool all this is, right? Because you've gone out, you've got a buried cylinder, right? And you really understand something about it. You understand where what the value of the signal is. You understand what the shape of the anomaly is. You get some sense about what the details are, and it all kind of fits together. And now the last thing, if I can find it, happened to the. Oops. So I'm looking for the tutorial. Where did that go?
The case history?
Yeah.
Click the preview below.
Oh, there we go. Thank you. So the example that you had was this one here. Okay, so if you look up here, so there's, I mean, that actually looks pretty much like what we just did with the app, right? It's kind of circular. And so you see where it is, and then you're asked to pick out the half width. Okay, so how do you pick up the half width of that? You got color bars. So now you have to calibrate color bars with numbers. If you look at the top here, it's about 78,000 nanotesla. So that's what this value is. And the background here is maybe 54,000. Okay? So now you've got that anomaly is going 78,000, 54,000. Okay, so that amplitude is 78 minus 54. That's 24,000 nanoteslas different, right? So now you want the half width and half max. So now we got to go. Half of this is 12,000. Subtract 12,000 from here, and that gives us 66,000. So now we've got to find 66,000 on a color scale. Well, kind of got it, but you can kind of see. So here's 64, 66. So 66 is just about the transition to the yellow. Okay. So now you take your ruler and you go from here to here, and you find out what that distance is, and you find that that's about 10 feet. Okay? If you take that, you divide it by 2, okay, that gives you 5 feet. Okay, so that's you're expecting that pipe better be 5. It seems like it should be about 5 feet below. If you look at what you've just done here with respect to the to the modeling, you see that, well, first of all, 5 feet. It was the measurements were taken 2.5 feet above the surface. If you remember that, and it said, oh, it should be 5 feet below. So that means it should be buried 2.5 meters or 2.5 feet below. And if you actually look at the what's in the case history, so they first of all they had some concrete, which is probably 6 or 8 inches, and then it was 6 inches below that. So it's at least a foot, maybe a little bit more, beneath the ground surface. So you can see, actually, you've actually done pretty well. You're probably within a foot of finding the top of that pipe. So that's it. You know what it is. You got it within, within a foot. You're good to go. So the only thing that is a little bit discrepant here is perhaps the value. So this is an anomaly of 24,000. When we were doing the calculations, we actually ended up with an anomaly of only like 4,000. So everything else seems to be okay, but there's a little difference in the size. So what, like when we're doing this modeling, what are the things that we could have done to reduce that discrepancy, to make this larger? Anybody? Yeah, Rita?
The actual thickness of the pipe was larger than the 1 centimeter.
Yeah, that's a good one. I think that's actually quite plausible that we did 1 centimeter here, but maybe it's closer to 2 centimeters or more. So that's going to increase the area, and that's going to go up. Perfect. Yeah. It could be. If you can't find anything else, you can always surround it by magnetized. But I mean, very often pipes are magnetized along their direction, and you've got a pipe buried here, so it could be magnetized to decrease that strength. Okay, so that's it. To summarize, we're not gonna actually mark that or take any marks off of that. If you did that, you get bonus. The main thing, and this is really important, it's just an ideal opportunity to understand because it puts everything together. And honestly, if you understand the pipe problem, and if you understand, okay, someplace, if I'm burying something on the surface of the Earth, and I've got this, I'm going to get a dipole, and it's going to give me this kind of a shape, and here's that's it. You nailed the mechanics. Okay, so with that, sorry, it took a little bit longer, but yeah. Lecture 2? Yeah. Okay. Well, said we need to make a reward system here for people who bring their names. You might think about that. Yeah. Oh, we do. Back in my office. Okay, cool. He's feeling left out.
So we're changing the gear. It's a bit too abrupt, but we're back to seismic now. Remember the waves and yeah. So we talked about a little bit of like a relationship between about amplitude. So consider we're putting in the wave and then how much energy we can get the reflection and refract it. Remember we talked about the reflection coefficient, which was R ratio between how much energy is reflected compared to the input, and transmission coefficient was Okay, naught over A2 is how much energy was transmitted. Right? So we talked about that. We know what are the definition of the coefficient, what happens if you got a larger velocity compared to this first layer, second layer. Now we're switching to another principle, which is actually very important. This is relationship kind of determines the angle of incidence, reflection, and diffraction. It's called Snell's law. So have you guys heard about that? I think it's pretty famous for a whole bunch of things, and especially for optics. Think about lasers and how it's transmitted, reflected. So the first law is let's start with the setup. So we're assuming a ray that coming in here, right? It's going to be reflected, and this is the incident angle, and this is the reflection angle, and some of them will be transmitted into a second medium. So this is a refraction angle theta 2. And the law of reflection, incident and reflection angle are same. Okay? That's the first law. And second law is that refraction, law of refraction. Okay? So what is the relationship between theta 1 and theta 2? And it's simply sine. Just gonna look that. Sine theta 1 divided by V1 is equal to sine theta 2 divided by. Like actually deriving that is not very trivial. You need to actually solve the boundary value problem, but we're not going to get there. So we're going to assume that's actually given, and those are right. Okay. Right? And so let's suppose this situation. So that's the equation. Okay. And then we have interface. We got V1 and V2. Okay. And this is incident wave. Okay. The incident angle was theta 1. And we know we're going to have reflection. Theta r. They are same, basically. And they're going to be some sort of reflection. Right? Okay, so which way it goes? Go up or go down? So it looks like this, it looks like that. Suppose V2 is large, then larger than V1. What's going to happen? Well, that's the equation. What tells you about that? Right? Okay. It's hard to imagine, right? But by looking at that equation, it's hard to imagine what's going to happen. You probably need to spend more time to actually put some values and what's going to happen, like, to imagine what's going to happen. But you can think about a car. Let's suppose this is a really rough road. The velocity is pretty low. Okay. And this is very nice road, like an asphalt. And then you have a car going like this. It moves, and it hits here, right? And this has higher velocity, right? So what's going to happen? It's going to turn like this, right? You can think about it. So you got higher velocity. It's going to refract it in like this, right? If you have a lower velocity, the car moves here. What's going to happen? This one has higher velocity, so it goes down. So that's it. Okay, so that's the relationship, and this equation basically tells how this is going to happen. Okay, they got two sort of ways to understand that equation. And you have a question? Okay, so that's the Snell's law, and let's look at this movie, and look at this sort of ray. Right? This is when V1, V2 is greater than V2. So, okay, so that makes sense, right? Like that was the line, and if you got a faster velocity, it refracted like this. Okay. And how about the other case? So you got V1 is greater than V2, it's refracted like that, goes down. So that's basically Snell's law, and then we can actually understand how waves are refracted and reflected at the interface. Okay, that's the Snell's law. So we got two relationships, and the Snell's law is talking about the angular relationship at the interface. And then we have coefficients of reflection and refraction, which talks about the amplitude relationship. Okay? So those are two important principles to understand seismology. And there is an interesting case. So I'm asking, what if when theta is theta 2, which is this angle, oh, sorry, this angle. Thank you. And what if theta 2 is 90? What's happened? What is sine theta 2? Volunteers? Oh, I think I've got it. John? Ah, perfect. So this is 1. So we can rewrite the sine theta 1 is equal to V1 divided by V2, and this is 1. Right? So we can actually compute what is theta 1 here. And can you imagine what it looks like in this plot? So what does it mean theta 2, 90? The ray path looks like this, right? So there's a wave propagates down in the V2 medium, but parallel to your interface. Okay? That's when theta 2 is 90. And we call this critically refracted wave. And that we're just going back. Can you see those guys? This linear curve? That's the critically refracted wave. And here, V2 is faster than V1. Right? So actually, you can see this coming up fast. So we call this headway. Right? And we can ask here, that's when it happened when theta 2 is 90. Okay? And so here, suppose V2, so V2 was larger than V1 before, right? Suppose what happens, V1 is larger than V2. Let's say this is 2,000 meter per sec. And that's 1,000 meter per sec. What happens? Does that make sense? Sine theta 1 is 2. Is it making sense? No. Right? That physically doesn't make sense. Right? So that actually tells you is there any refracted wave here? Critically refracted wave? Cannot see that, right? So that tells you that doesn't physically make sense to make a critically refracted wave when V1 is larger than V2. Yeah, so there are some resources. So those are the physics, and there are some resources that you can take a look here. I think I just need to finish, but here's some in the second lecture we're going to talk about the travel time, and here's a bit of motivation that I want to tell you why that's important. And suppose this is the seismic source that we're putting in. And then we're measuring the seismic signals, which will have a direct wave reflected and refracted around here, right, at the receiver location. And what do we want to know? So let's suppose we got 2 layers, alluvium and basement. Well, you guys are engineers. You guys probably really want to know where's the basement, right? And what are the elastic properties of the basement and also the top layer. Okay. So those are your goals. And unknown here is P1 is unknown. P2 is unknown. And also the thickness set is unknown. Okay. So that's the information that we want to extract from the data, from seismic data. Okay. Those are the motivation. And simply what they put, basically the equation that we're going to use is this. T is equal to D divided by V. So T is the travel time, right? So data is the time. And so this is the data. And we know the D sometimes. And then we want to know the V. So those are the goals for the other lectures. And this is actually just real data, right? Because you're actually going to measure. By looking at that, or interpreting it, we want to know what is the V1, what is the V2, what is the thickness of the layer. I'm pretty sure we can do that at the end of this course. That's the motivation. And I think that's it.